tiny planet in a tiny galaxy. But Einstein's equations apply to the vast leagues of stuff in between, empty space. As physicist Pedro Ferreira explains.
Now, let's imagine that this enormous library is our visible universe. And we know that the universe is sprinkled with galaxies, and I really mean sprinkled. There's a lot of empty space around each galaxy. Let's take our galaxy, the Milky Way. It would comfortably fit in a full stop in Stephen's book.
Our galaxy is microscopic compared to the gigantic tracts of empty space that dominate the universe. But Einstein showed that all that empty space turns out to have some remarkable properties.
Let's imagine that this basketball is a celestial object like a star, okay? And let's imagine that this bookshelf with these books is space. In our classical view of space, it would be rigid like this. It would just be this static thing, this thing that is unresponsive. But in our modern view, this star, as it moves through space, it warps it, it dents it, it bends it. And other objects that then move through this space will feel this warp, will feel these bends, these warps, and will move according to that. They won't move in straight lines. They'll feel these bends and they'll curve.
The fact that big objects, like stars, can actually bend and curve space is now an everyday notion to astrophysicists like Kim Weaver.
What we're talking about in terms of astronomy and cosmology are objects that have a huge amount of mass. A planet-sized object, or a moon-sized object, or a star-sized object. The mass of this object bends space around it. If the ball here that is at the center of the sheet is representing the sun, and this penny is representing a planet like the Earth, then you can use the penny to demonstrate how the Earth orbits the sun.
We think the force of gravity makes the heavens turn. What physics says is actually going on is planets orbit stars because they're trapped in areas of curved space. The Earth is actually rolling round and down into a dimple in space-time caused by the sun. The penny rolls in quickly, but of course, it'll take the Earth billions of years to hit the sun. The Earth also causes space to bend around it. What we think we feel as the force of gravity is, in fact, the strong curvature of space around our planet. According to Einstein, when astronauts slip the earthly bonds of gravity, they're actually escaping the strong curvature of space. But Penrose and Hawking were about to do more than just bend space. They were going to turn it right back in on itself and conjure up black holes. Young Stephen Hawking was electrified by the work of Roger Penrose.
It just marks time outside, and I'm going to draw this.
Many physicists thought black holes were just a crazy idea, but Penrose had proved they must exist. It takes the death of a massive star to make a black hole. As a star burns down, all of the waste products are drawn into its center. The center of the star becomes so heavy that a teaspoonful would weigh more than a mountain range. All the while, around it, space is being curved back in towards the center. Finally, this curvature of space, the effect of gravity, becomes infinite. Not even light beams can escape. Around the ultra-dense center, there forms a sphere of darkness. that we now call a black hole.
If we take something like the Sun, if that were to form a black hole, then the size would be about a few kilometers. If the planet Jupiter were to collapse into a black hole, it would have a size of a few meters. So this black sphere here will be a good representation of what the black hole formed by Jupiter would look like. If the planet Earth was to collapse to a black hole, it would be even smaller. It would be a few centimeters in size, so that might be a representation of the planet Earth.
But Penrose hadn't just shown that the Earth could be compressed to a black hole the size of a tennis ball. What excited Hawking was that Penrose had proved, using Einstein's equations, that at the center of a black hole there was a plug hole, down which matter, space, and time disappeared. The plug hole had a fancy mathematical name: a singularity. Hawking was excited and mystified.
In 1965, Roger Penrose showed that if a star collapsed below a certain critical radius, it would inevitably develop a singularity, at which time would come to an end. At first, I didn't understand either the significance or the proof of this result.
Hawking became obsessed with understanding the singularity. It was a strange choice of specialist subject. A young man who'd been told he had 2 years to live was wrestling with a point in space where the universe disappeared out of existence. And amazingly, Hawking turned the plug hole of death on its head.
Now what Stephen showed, the first thing he did in this area, was to show that the same argument can be used in the reverse direction of time. This argument applied to time going that way.
Hawking had the brilliant insight to reverse Penrose's equations and apply them not just to a black hole, but to the entire universe. If bits of space could disappear down the plug hole of a singularity, perhaps everything in the universe had originally appeared out of one. In what was his PhD thesis, Hawking made a huge breakthrough. He proved that the universe had to have appeared out of an incredibly tiny single point. It was a fabulous result, but it was also the science equivalent of shooting yourself in the foot. He could prove the universe started from a tiny single point, but frustratingly, not how or why. It seemed to many that this inexplicable, sudden appearance of the universe, expanding out of a microscopically tiny point, had to be a miracle.
There are two attitudes one can take to the results of Penrose and myself. One is that God chose how the universe began, for reasons we could not understand. At a conference on cosmology in the Vatican, the